Okay, so 5.2, we did the notes up here. Now we have to do 4 and 5 on the bottom here. So originally we labeled this as rate law. So this is the equation for it. This is the rate constant. Here's our concentrations of reactant A and reactant B. Hi, Miss B.
Are you recording?
I am.
Sorry.
That's okay.
Hi, guys.
What's up? I think I can pause it. Hang on. Okay. So this is the rate law. Here's the concentrations of A and B. So, and then M and N are the exponents. So in these types of problems, you are going to be looking at like tables of data, and you are going to be trying to figure out what M and N are. So in the tables here, typically they have, let me zoom in. They have experiments, so 1, 2, and 3. They have the concentrations of the reaction. So our reaction in this one is NO, and then we have O2. So here's the concentration of NOs and the O2 reactions for each trial or experiment. And then here is the rate for each of them. So given all this information, we need to figure out what M and N are. So how you do this, it's kind of it's not really tricky. It's not too bad. On the back side, though, let's go over this because you're going to need this information. So according to reactions for kinetics, you can have an overall rate of 0, 1, 2, or 3. So that means overall, as you add those exponents together, and if they add up to 1, they add up to 2, if they add up to 3, that is your rate. This is how you would write your rate expressions for them. So if you have an overall rate of 1, you just take the rate constant times the concentration of your only reactant. You could have rates for 2. You can have A times B, or you can have A squared. And then if you have an overall rate of 3, you can have A squared or B. You should notice that the exponents add up to the overall rate. So we have 2 plus 1 technically is 3. 2, and then 1 and 1 is 2. So if you have an overall rate of 2, you can actually have 2 different options for that. These are the units. So depending on what rate you have, the units do change. So here is how we are going to determine on the front side. So if it is 0 for your exponent, that means the rate number is going to stay the same, but the concentration is going to change and there's no pattern to it. If you have 1 for your exponent, that means the rate doubles and the concentration also doubles. You can have the rate triple, the concentration triples. They just go up together at the same time, or I guess they could go down at the same time. If you have a rate of 2, that's kind of the trickier one. That means that the reactant concentration will affect the rate to the square. So that means if your concentration is 4, it goes off by a difference of 4, which we'll do some problems with. That means if you take 4 squared, the rate should be a difference of 16. Okay, and then same thing down here, that's how it's going to affect it. So on question 4 here is our data, and then let's start answering this stuff. Okay, so it says determine the order of the reaction with respect to each of the following reactants. So what this question is asking, so we need NO. So I'm going to label that M, and then we need O2. So what we are trying to do here is we are trying to solve for M, and we are trying to solve for N. So the way that you do this is you pick which one you want to solve for. I'm going to do NO first because it's listed first. So I go to my data. I find here's NO, so I'm going to be looking at the concentrations of NO for this. And you go to O2. So which experiment should I look at? Well, there's kind of a thing you have to do. Gosh. You need to look at O2, and you need to find which experiments do the concentrations of O2 are the same. So in experiment 1 and experiment 3, they both say 0.0300. So that means when I look at NO, I'm going to look at 0.02 and 0.0600 because those are the 2 experiments where O2 remained constant. So we want to look at NO, so we need to find which trials does O remain constant so it doesn't affect the exponent. So I'm going to write this off to the side. So for NO, for my concentrations, it went from 0.0200, right, in experiment 1. I'm sure you can see this. And then in trial 3, it went to 0.0600. So if it goes from these two numbers, I would say what? It was tripled, right? Times 3. So this was tripled. Okay, so the concentration was tripled. Then I have to look at the rate. So for NO, the rates are all over here. I have to look for 1 and 2, or 1 and 3 again, right? So I'm picking the same row. Okay, so I know it's kind of hard to see, so I'm going to write them out. So I'm looking at these two rates and how do they affect each other. So for the rates, it goes from 8.52 times 10 to the negative 2 to what? 7.67 times 10 to the negative 1. So that's how do these affect each other? So I'm going to go to the flip side here. Well, if the rate stays the same, so if it's 0, if the exponent's 0, the rate has to stay the same. So these clearly are not the same number, so it does not stay the same. Okay, so can't be an exponent of 0. If the rate doubles or triples, that means the concentration also has to double or triple. So it tripled. So in order it to be rate or an exponent of 1, that means this has to triple. You could do this in your calculator, but this does not triple. Okay, so that's not an option. So that means the only option we have left is it could be an exponent of 2. Well, let's make sure that it does. So we said that the rate or the concentration tripled. So here, 3 times 3, it tripled. That means if I take 3 squared, the rate should have been times 9. So in my calculator, shoot, I should have had that out. Oh gosh. So if you plug this stuff into your calculator, second e to the negative 2, that means this should be times 9, right? Because 3 squared is 9. So 8.52 second e to the negative 2, let's times it by 9. It gives me that number. Well, if you put it in scientific notation, oh, it's very, very close to that, right? If you round. So that means this was 3 squared, which was 9. So if I go back to the front here, just so you know, right? If it was 3 squared and the rate was by a factor of 9, that means my exponent for NO is going to be 2. So that means my M right here, I'm going to change that to 2. Okay. Now, I'm so sorry to inform you this, but you have to kind of know these. There's no sheet that you're going to get. Okay. So hopefully 0 and 1, I think, are kind of like okay to memorize. And then the way I like to look at it, that if it's not that, then the only option is 2, okay, for the exponent. Okay, so we got NO. Now we have to get the concentration of O2. So I'll do that in a different color so you can see it. Okay. O2. So I go to the data here. I'm going to zoom in. Jeez. I can't even see it myself. O2. I need to find these concentrations now. So I'm going to go over to NO. Where does it remain the same? Well, this is 0.2 and 0.2. So that means I have to look at these two numbers for O2. Okay. So O2's concentration. So it goes from 0.0300 to 0.0900. Okay. So how do these, no, you can't even see that. Why? I hate this thing so much. It's so stupid. Oh, sorry. Goes from 0.0300 to 0.0900. So I would say that what, tripled? Yeah. Okay. It tripled. Okay. Now I look at the rates. Again, it's for experiment 1 and experiment 2. So I'm going to look at these rates right here, these two. So I'll write those out for you. So the rate is what? Jeez. 8.52 times 10 to the negative 2, and it's 2.56 times 10 to the negative 1. So that means this is tripled. Okay. Oh, shoot. How would you know that? Okay, well, let's slow it down a bit. Okay, so I go to the back side. It says the rate stays the same for if I want the exponent 0. Here are my rates. Those clearly aren't the same number, so it can't be an exponent of 0. Next one, rate triples, which it does. That means the concentration triples, right? We said it tripled. Does the rate triple? If it does, then it's an exponent of 1 then. So I plug this in my calculator. You just take them divided by each other. me just show you. Divided by -1. Oh, it's in the exponent. Shoot. Hang on, I did not type this in right. If I take 8.52, don't divide it by each other. I don't know why I said that. You take 8.52 times 10 to the -2, it triples, so times 3, I get this number. This number is the same exact number, but in scientific notation. So that means the rate also tripled. So they both tripled the rate right here and the concentration. So if I go back here, if they both triple, rate triples, concentration triples, that means the exponent is 1. So that means O2, the N, is now 1. Okay, so now we got that. Part E says write the expression for the rate law for the reaction. So I'm going to say rate equals, right? So now I'm just using this up here. Rate equals, K is a constant. We don't know what K is, so K. Our first reactant, I believe, right, is NO. So instead of writing A, I'm going to write NO. It has a 2, right? That's what we figured out. And then times B. B is our second reactant. We figured that out, or it told us that it was O2. And raised to the 1, you could put 1, or you don't have to write 1. Typically, they don't write 1s. Okay, so that is how you would write your rate expression or your rates law. Then the last part here says determine the value of the rate constant for the reaction indicating units. So now they're asking us to solve for the rate constant. Rate constant is K. So we need to solve for that. So what I would do is you have to go up to the rates up here of formation. So the rate of formation of NO2, you can pick any of them. I usually pick the first one right here. So it says that it's 8.52 times 10 to the -2. That's our rate, okay? So I just picked the first one. You can pick any of them. I really don't care. Now it says it's for NO2. So when we decided to do our rate law, it's only for 1 mole. So if I go up to NO2, NO2 has 2 moles. If it had a 1 there, then I can just use this value. But it doesn't. It's for 1 mole. So that means I'm going to have to divide for 1 mole. So I'm just going to divide it by 2. If I divide that number by 2, what do I get? I can't do mental math right now. Oh, God. 0.0426. Okay, so that's my rate. I'm using this equation up here. K is what I'm solving for. NO2. Okay, well, we know the concentration of NO2, right? It says in the table. So I use the rate from the first experiment. So that means I have to use the 2 concentrations from the first experiment. So NO is 0.0200. And again, raised to the second power. So I'm just plugging in this equation. And then times O2. O2 is from the first experiment, 0.0300. Okay, can you solve for K algebraically? Yes, you can. I'm just going to write the answer here. So what you would do is you would take 0.0426, divide it. You know what? I won't just write it all out because who knows. Divide by these 2. Right? Because it's being multiplied on that side. Sometimes we can't do algebra. I can't do that sometimes. Equals K. Okay. Now, you plug that in your calculator. For K equals 3.55 times 10 to the third. Oh, shoot. 3.55 times 10 to the third. Now, we need the correct units. So for the units here, we need our overall rate. So let me flip back. Here are my units, right? Well, I need the overall rate, right? That's m plus n. Those are the sum of my exponents. So flip to the front. 2 plus 1, right? My m and n. 2, did I say m and m? m plus n. 2 plus 1 is overall 3. So if I go down to my third order, that means my units are m to the minus 2, s to the minus 1. So then for my units, I'm going to put m to the minus 2, s to the minus 1, and I just solved for k. Okay, so that is how you do that. I was actually going to do number 5, but I think I might have you guys just do that on your own. Yeah, I think you can do it because it is multiple choice. Yeah. Okay, so that's going to be for homework with also the notes. You can do it. I believe in you. That's it. And the other video should be on 5.3.